everyone. Thank you for coming. I'll get up and do it officially. So today we have Roland Timmerman, and we knew each other from PhD, where we were in the LOFAR research group together. And now he has moved on to Durham University in the UK, still working on LOFAR, mainly on the International LOFAR telescope. So getting very, very high resolution radio images at very low frequencies. So can do a lot of cool AGN science with that. And he will speak to us about it today. And he's also been joining me on Journey Through the Universe classes this week, which has been a lot of fun. This morning we did a few classes on the solar system. And yeah, kids really loved it. It was cute. And my other visitor is Eric Osinga. He is from the same research group in Leiden, where I did my PhD, and now works in Toronto as a postdoc. Yeah. So thanks for coming, and take it away, Roland.
Thank you so much. All right, it's really nice to be here and share some of my sort of recent work on LOFAR. So most of what I do is on the field of galaxy clusters. So let me just very briefly introduce galaxy clusters. So if you look, of course, at the universe on the largest scales, you'll find that galaxies are not distributed uniformly, but they have a pattern to it. The cosmic web, of course. So you have regions with fewer galaxies, like voids, which are surrounded by regions with a few more galaxies, like walls and sheets, which then connect into filaments with even more galaxies, and those filaments in turn connect into nodes of the cosmic web, where if you point an optical telescope, you will find something that looks a little bit like this. It's a galaxy cluster. Typically, what you see in a galaxy cluster is one dominant central galaxy surrounded by hundreds up to thousands of member galaxies. And the interesting thing about galaxy clusters, to me, is that at first glance, it very much looks like a sort of collection of galaxies that just happen to be in the same environments, if you will. But if you actually look at where the mass is, you'll quickly find that that's actually not a very complete picture. If you look at all of the baryonic mass, so not even considering dark matter and all of that, you'll find that only a few percent of all of the baryonic mass is in stars in galaxies. A few more percent is in gas and dust and all of that. But actually, the majority of this pie chart here is in intergalactic gas. So all of this sort of gas that is in between galaxies in a galaxy cluster, which we know as the intercluster medium. And that's essentially our first hint that these are really, you should think about galaxy clusters as systems rather than just collections of galaxies. Because it's a very, very hot gas, this intercluster medium, we typically only see it in the X-rays. So if you look at an X-ray image, like for instance this one here, taken with Chandra, you see that basically we have this sort of glow from in the X-rays that permeates the entire cluster environment and shows you where all of this sort of, or most of the baryonic mass actually resides. So it's a very, very diffuse, very hot component in a galaxy cluster that permeates the entire environment. And actually the ICM is so sort of important to a galaxy cluster that we can even typically characterize what galaxy clusters are doing based on what the ICM looks like. So if we look at the evolution of galaxy clusters, they form hierarchically, starting in the protocluster regime. So in the protocluster regime, we do have galaxies that are sort of approaching each other, starting to sort of gravitationally bind together. But typically we also see in the ICM that it's really not a single halo yet. It's really much more of a sort of blobby structure that sort of starts to coalesce. Like you see, for instance, here in the spiderweb protocluster at redshift only 2, which is high redshift for galaxy cluster, but not high redshift for quite a few other people, I guess. After you have your protocluster regime and you do form a nice ICM, there's growth through mergers. These are simulations by John Zuhon, where you see, for instance, these two examples of galaxy clusters colliding and merging together. And as you can see also, there's a lot of shock waves in the ICM, a lot of turbulence that, of course, also follows from these shock waves. So these merger events are also really, really key events to the history of a galaxy cluster, mainly because they really affect the ICM quite heavily. And after you have gone through all of your sort of merger scenarios, you end up with the final box here, which is sort of relaxation and cooling. So after you've had your sort of mergers and the system sort of settles down again, the sort of dominance effect at that point becomes the emission of this X-ray radiation that I mentioned before, which allows the ICM to also lose energy and sort of start to cool down over time. And if you look at this cooling exactly, you can make a very quick calculation that basically says you have some amount of like ICM gas that has sort of internal energy. it emits a certain amount of X-rays. So from the ratio, you can sort of estimate on what kind of time scale should this ICM gas start to cool down. And if you look at it, you'll typically find that for most galaxy clusters, if you look at the inner 100-ish kiloparsec, the cooling time starts to drop significantly below the Hubble time, basically suggesting that on time scales shorter than the age of the universe, its ICM should in principle cool down. And once it cools down, it can do all sorts of things like accrete onto your central galaxies and form stars and feed black holes and all of that. However, there's a few small details about that. First of all, we don't actually see typically starbursts on the order of a sort of 1,000 solar mass per year figure, which you would expect purely based on the cooling luminosity of the ICM. And secondly, we still see the ICM today, even in central regions. We do see that it cools down. We do see it's typically the formation of sort of cool cores, but we don't really see that the ICM disappears, if you will. So clearly, there is something that actually sort of offsets this cooling through X-ray radiation, something that sort of reheats the ICM and prevents it from actually cooling down at the rates that you would expect, purely based on the X-ray. And of course, we know that to be HGN feedback. So primarily in the central galaxy, the central dominant galaxy of a galaxy cluster, we have a really quite supermassive black hole that, of course, feeds on some of this cooling gas, and then it can do primarily two things. It can either produce radio mode feedback or mechanical feedback, if you prefer, which is the feedback mode where some of the matter that flows towards the supermassive black hole doesn't actually cross the event horizon, but it instead gets sort of funneled into relativistic jets that shoot off out of the environment. We think primarily driven by magnetic fields, but we're still working on that. But you essentially end up with these two jets that shoot out of the environment, out of the galaxy itself, into the intercluster medium, and thereby reheat essentially the ICM. Alternatively, there's your quasar mode feedback or your radiative mode, which is based much more on the sheer radiation pressure of the accretion process at the central supermassive black hole, which also can blow away all of your surrounding gas and dust. Typically, the quasar mode is much more contained within the central environment, whereas the radial mode, the jetted mode, can really just completely launch out of your galaxy and shoot off into the ICM. If you look at the balance between the heating and the cooling, so we have the cooling here on the horizontal axis and the heating on the vertical axis, you'll see a very, very nice correlation here. If you follow the 4PV line, we'll get to that one, you'll see that typically actually they're really quite in balance, showing that the heating that you actually get from the supermassive black hole through this radio mode feedback here actually typically is enough to indeed offset the amount of like X-ray radiation that we do see. So we know that there's a sort of balance between the heating and the cooling in galaxy clusters. So the sort of short summary of all that is that galaxy clusters really are not just collections of galaxies, but they're really strongly interacting systems where a lot of astrophysics comes together, all the way from galaxy evolution, HN feedback, gas heating and cooling, magnetism even, cluster merger scenarios, shock and turbulence. It all comes together in the galaxy cluster, which is why I think also personally that they're really quite interesting environments. And secondly, the reason why I also think they're really interesting is because in the radio, typically, they're also really prominent targets. So this is an example of an image of a galaxy cluster made with the VLA, I believe. And we can also see multiple components here. We have a sort of diffuse halo right around there. So this is a halo of essentially relativistic particles that just permeate the environment, quite similar to the ICM. We have these relics, which we believe are formed when we have these particles in the halo getting reaccelerated, getting, for instance, by like shock and turbulence, making them appear bright again. We have a couple examples of these AGN. So here's a few AGN, here's an AGN, there's an AGN. And you can see these jets all feeding into the sort of larger environment of the galaxy cluster. So from the radio also, the galaxy clusters can be really quite spectacular targets and a really good way also to study all of these physical phenomena. And a tool that I use primarily is the International LOFAR telescope, which is mainly a European array. We have we're observing at very, very low frequencies. So we have the LBA operating just below the 100 megahertz regime and the HBA operating just above the 100 megahertz regime. So basically every single station of LOFAR has both of these two antenna types. So we have the HBA tiles, we call them, are these structures there. And then the LBA are really just sort of separate dipoles. And every single station in Europe has both an LBA and an HBA component to it. So you can always choose whether you want to observe at low frequencies or even lower frequencies. What makes LOFAR a really quite effective instrument, and this has also come back the talk, is the fact that LOFAR has baselines ranging all the way from a couple dozen meters to 2,000 kilometers. And that's a really quite unique capability of an interferometer. Most interferometers are quite similar physical separations, like for instance the VLA or the GMRT, or you name it. They're all on typically quite similar-ish baselines. They do always have short and longer baselines, but this range in scales is really quite unique of LOFAR, and also makes it a really quite powerful instrument. We have a total of 52 stations, so that's also quite a lot. Most of them are located in the Netherlands around there, but we also have currently 14 located throughout Europe, soon to be 2 more even. And what makes LOFAR also a really quite effective instrument is multi-beam observing capabilities. So LOFAR, being what we call sort of software telescope, doesn't have any moving parts. So basically that also means that if you want to point in different directions, you absolutely can. You just have to do more math. But we do have the computational power actually to observe in multiple directions, so that you can also indeed survey a very large part of the sky at the same time. Or if you want, you can keep an eye on like one target while you're still surveying other parts of the sky. In combination with that, LOFAR also has a very wide field of view. Depends a bit on if you use LBA, HBA, different station types, or whatever. But typically it's on the order of a few square degrees, maybe even up to a couple dozen square degrees. So combined with the multi-beam observing capabilities, it's really quite easy to survey a large part of the sky quite efficiently. In terms of what you can see with LOFAR, essentially we're confined to the northern hemisphere. Declination 0 is really a sort of hard limit for us almost. So if you ever have a sort of target that you think, hey, let's see if there's LOFAR possible for it. If it's northern hemisphere, we can do it. If it's southern hemisphere, then it's basically out of LOFAR's reach. And we're currently also working on the LOFAR 2.0 upgrade. So LOFAR officially launched around 2010-ish. It's been going on for a couple of years now, and now we're working on the LOFAR 2 upgrades, basically implementing a lot of upgrades to the hardware, a lot of lessons learned over the years that we're now also implementing. And this also includes the expansion of the array to both Italy and Bulgaria. So LOFAR is going to be even larger in the very, very near future, and even more sensitive and capable and all kinds of things. So if you look at what LOFAR actually looks like, the very center of the array has what we call the SuperTurp, which is this 300 meter sort of circle containing 6 stations. These give you sensitivity on the order of a couple of arc minutes, fraction of a degree kind of scales. Surrounding that SuperTurp, you then have the Dutch core station. So you see one there, one there, one there, there. These give you sensitivity on the order of a couple of arc minutes, mainly. Surrounding the core stations, you go to the Dutch remote stations, and these give you sensitivity on the order all the way down to like, for the HPA, for instance, which is the main workhorse, 6 arc seconds, which is already, for a very, very low frequency interferometer, a quite competitive angular resolution. That's similar to what you will get, for instance, with like SKA low, for instance. So that's already a very, very competitive resolution. And also, this Dutch array has been the sort of main workhorse of LOFAR throughout its lifetime, including, for instance, for the LOFAR 2-meter sky survey, which has been going on for over a decade now, has 15,000 hours of time on sky, basically covering most of the northern hemisphere, which you can all see in this diagram right here. It's a total of 20 petabytes of data that was processed for this single survey. And as I mentioned, because it uses the Dutch stations, it offers you a 6 arc second resolution across basically the entire northern hemisphere. And currently for LOTS data release 3, which is going to be out very, very soon, we have 13 million sources included in the catalog. So that's a really quite, that's currently the largest radio survey out there. It's actually larger than all of the other surveys combined, including data release 2 of LOTS itself. Yeah. And what is very interesting about LOTS and about LOFAR in general is that at this 6 arc second angular resolution, about 92% of the sources just remain unresolved. So they just appear to LOFAR essentially like a point source. And what's also very interesting is that for the purpose of the LOFAR 2-meter sky survey, even though it actually only used the Dutch stations, every single observation also included the full international array. So in principle, you can go back to all this data and make use of international stations and get an angular resolution down to around 0.3 arcseconds in the HBA. So that's a factor of 20 more compared to just a Dutch array. And if you look at what it actually looks like, it's a nice example of an AGN. This is the image from LOTS showing you sort of extended blob-like structure. And if you look at the international array, you actually see a very, very different picture, showing you a very nice bright AGN in the center. These two radial lobes towards the north and the south, and you can even see a bit of like structure within these radial lobes. So the angular resolution that you can gain by actually including all of the international array is really quite transformative. So basically, the structure of the talk is going to be basically covering all of these spatial skills that LOFAR has access to, all the way from megaparsec skills down to a couple dozen parsecs in the context of galaxy clusters. And I'll start on the megaparsec end with radio halos. So radio halos, as I mentioned before, are these sort of kind of puzzling structures in the sense that we see in the environment of a galaxy cluster this sort of cloud of radio emission. So we have typically a sort of central galaxy, and then surrounding that, you can either have a giant radio halo or a mini halo. The giant radio halos tend to be sort of megaparsec-ish scales, and the mini halos tend to be sort of 100-ish kiloparsec scales. And the kind of puzzling thing about this is that to get a halo, you essentially only need two ingredients: the magnetic fields and some relativistic charged particles. Now, magnetic fields are kind of everywhere in the universe, so they're not necessarily too surprising to find. But the relativistic charged particles actually are. And the reason for that is that simply in these sort of completely empty regions of the galaxy cluster, apart from the ICM and apparently some charged particles, there's really nothing else that typically obviously accelerates particles to the kind of energies that we see with our radio telescopes. So typically, we believe that most of these charged particles originate from black holes, for instance, and they diffuse away over hundreds of kiloparsecs into seemingly empty regions of space where they can still emit radio emission quite substantially. And that's a quite puzzling phenomena to observe. So there's basically two models that we're trying to figure out here. One is the hadronic interaction model. So that's the model where you have cosmic ray protons from the supermassive black hole, which do lose energy slower, eventually at some point colliding with these thermal particles from the ICM, and then producing this sort of particle shower that includes highly relativistic electrons that you can then see with your telescope, or alternatively, having simply the turbulence in the ICM being able to reaccelerate particles to these energies that we actually do see with our radio telescopes. And a lot of work is currently going into trying to figure out which of these two models is true. Are they both true? Are they in some ratio between each other, true or not? But that's the sort of main puzzle here with radio halos. We do already believe that there's quite a bit of information to be gained from the dynamical state of these clusters. So if you look at merging clusters or these clusters that's recently-ish merged, you do typically see more of these giant radio halos. So that's halos that have a much wider reach. And we believe that it could be that sloshing due to recent merger events cascades down to turbulence, which then produces these giant radio halos. And that's much more in relaxed clusters, you find these mini halos. So you end up with a picture that, because there's no turbulence substantially in the environment, it's really only in the sort of central region where the cooling becomes very, very strong, that you also induce a lot of turbulence from this cooling flows, and that you end up with the production of a radio mini halo. That is at least a picture that we kind of had until a few years ago. Until one of these sort of very classical relaxed clusters, the Perseus cluster, became our target. So we have an observation of the Perseus cluster, showing you the high resolution image here on the left, showing you the part AGN, these two radial lobes. If you zoom out a little bit further and go to more slightly lower resolutions, you will see the central area here again, but then also surrounding this, the mini halo. First of all, the mini halo actually shows quite a lot of structure. It's really not a sort of diffuse blob like you might expect, but you actually see sort of sharp edges in the mini halo. You see sort of filaments here, spurs, a lot of structure in the mini halo, much more than you might expect. Even a few examples of member galaxies of the cluster launching jets into the environment, which also then sort of merge into the mini halos. So already that's a quite nice image. If you zoom out even further, you surprisingly find that actually there's also a giant radio halo in the Perseus cluster. So this shows you the 26 arcsecond map and the 80 arcsecond map, which are really quite spectacular maps, I believe. We see, for instance, here this very, very distant galaxy also having a sort of tail that connects back to the central region, also quite nicely shown here. This beautiful northern tail also connects into the mini halo, but also we can very nicely see this very large halo also in the Perseus cluster, which is quite surprising because this really was one of our prototypical relaxed clusters that didn't have a recent merger event. And now to our surprise that there's also this giant structure seen in the Perseus cluster. And we have since then also already had a few other examples show up where we see these giant structures, even in what we sort of know canonically as relaxed clusters. And just to show you why LOFAR is really a quite key component here, if you look at LOFAR image compared to previous images, you'll find that actually the sensitivity of LOFAR to these very, very larger scales here is very, very important. So LOFAR was able to go all the way down to essentially the sort of pixel scales in here, but also pick up all of the emission on much, much larger scales, which previously was simply missed. So the fact that LOFAR was able to give us both the high and the low resolutions was really quite key to having us be able to pick up this giant radio halo. Also, we made a recent quite nice discovery in Sparks 1049. We actually discovered a mini halo at a redshift of 1.7, which is really quite high redshift. That's double the previous record. And that's in turn really quite surprising because, first of all, yeah, we were able with the shorter baselines to actually see this mini halo, and using the longer baselines, figure out like, is this emission actually compact in nature or not? Turns out that none of this emission related to what we call the mini halo is actually compact. You can really prove that it's very, very diffuse emission. And this shows us that essentially we must have had some kind of like either reacceleration or hadronic process already in place really quite early in the universe. It's one of these examples of structures like sort of early galaxy clusters already showing quite a bit more maturity than you might expect, really quite early in the universe. So that's a really quite nice result. And also this already means that unless this is the highest redshift you can go to, this already means that you must have some kind of like cosmic ray population already in the environment of a galaxy cluster, already into the protocluster area as well. Then I want to go on to the next chapter, which is on slightly sort of smaller physical scales, which is radio lobes. So if you look at what actually goes on if you have the central supermassive black hole launch its two jets into the environment, is that you produce, first of all, very, very nice collimated jets, which then form these sort of larger radio lobes. And the really cool thing is that if you look at the X-ray, you'll actually find that wherever you have these radio lobes, you don't have the X-ray emission. So the radio lobes essentially push away the material in the ICM and produce these sort of bubbles or cavities, if you will, in the ICM environment. You can also sort of recognize here that around these sort of radio lobes, there's a sort of lack of the blue emission, of this X-ray emission in both of these examples. So you can very nicely see that these radio lobes essentially push away the surrounding gas. And that's really one of the ways in which you can also measure the energy output contained within these jets. Speaking of, just a very quick amount of mathematics, not too much, hopefully. Basically, you can make the quick argument that if you observe these two cavities in the ICM, that the total amount of energy that you have within those cavities essentially is the combination of the internal energy of those radio lobes plus however much work it takes to inflate such a cavity against external pressure from the ICM. And that turns out to simply be 4 times the pressure times the volume. So it's fortunately a quite easy calculation to make. You just need to know the volume of these cavities and the pressure in the environment, and then you can divide it by some estimate of the age of these structures to get to a sort of average power level. Typically for the age, you can estimate, for instance, that these structures propagate away from the central supermassive black hole at either like the speed of sound in the medium, or that they like rise away sort of buoyantly because the radio lobes actually are lighter than the surrounding gas. You can also model them as sort of buoyant structures, which then also propagate away from the central environment. Typically, those numbers are really quite similar, so it doesn't really matter too much for the final numbers. But that's just a very quick impression of just like how would you typically estimate age of a radial lobe. Typically, it comes down to most of all just measuring pressures and volumes of these structures. That becomes more difficult towards higher redshifts. So if you go towards redshift of, like, for instance, 1.2, it becomes really quite difficult to measure these structures. So here's an example of a total X-ray map of the ICM. This is Chandra, so it's already really quite good. And you can already tell that it's really quite difficult to already constrain what the ICM looks like in the first place. You can make it a little bit easier for yourself if you sort of subtract a sort of smooth model, which is done here. Then you end up with what the author calls here 2 potential cavities located there and there. You can already tell it's a bit difficult, it's a bit questionable. It becomes difficult to even identify a cavity. Measuring the volume is really just not in the cards at this point. So if you really want to go towards these higher redshifts and still be able to measure the heat sink produced by a supermassive black hole in the cluster environment, you really need either very, very deep channel, which they're not going to give you, or something else. And we believe that also low frequency radio can be really quite key here. So this shows you the image from before, left showing you the previous image at around 300 megahertz, and on the right hand side the LOFAR image at about half that frequency. And you can see also that if you use the LOFAR, we typically see a lot more of these radial lobes, to the point that you can actually say that you might reasonably call it the complete radial lobe. The issue is typically that a lot of these particles in these radial lobes, they decay energy over time, so they typically lose the highest energies first, meaning that also at the highest frequencies you will lose them first. So you really need to go towards very, very low radio frequencies to actually see the complete population of this radial lobe. And you can also see here very, very quite clearly that it's a really quite substantial difference if you go towards the lower frequencies. And this gave us the sort of hint of like, is it possible potentially to not use the cavities volume from the X-ray, but to instead use the volume of the radial lobes if we're sensitive enough on that end. So the picture that you basically get very, very simply here is that you combine both the radio and the X-ray into one measurement rather than just purely using the X-rays. If you combine them together via this way, you basically get the volume from the radial lobe, the ICM pressure from the X-ray, and then you can combine those and propagate into a average cavity power. That of course needed a bit of testing, so we did confirm with LOFAR on a sample of galaxy clusters, do you actually get a consistent volume measurement between the radio and the X-ray? And the good thing is that actually you do end up with most of these clusters lying very, very nicely on the one-to-one line. The scatter here is relatively good. It's only 0.30 dex compared to what people previously were able to get purely based on like radio, which is a bit higher scatter. This really means that currently this is the most accurate way of like actually getting to these kinds of measurements at all. So what we learned from this is that by comparing the radio and the X-ray, we can actually tell that using the low frequency radio observations, we can actually detect reliably the complete radial lobes rather than just a part of it. That then allowed us to go on to higher redshifts. So we basically used methods on a sample of these higher redshift targets to see, what would actually happen if we put this in practice, and we actually go to like a few targets where we no longer see clear cavities in the X-ray. So we actually measured the amount of power in the cavities per redshift, and using a very, very quick test, essentially, we already were able to add these 3 data points to the plot. So already in sort of higher redshift regime, that's already contributing quite a bit of like data in that population. And also you can see that because we're able to go towards also much smaller scales. You no longer need multiple pixels together to produce a cavity. We're also able to go to much weaker cavity systems, essentially. So we're able to also see much more of the population, not just the sort of very, very strong systems, but also the much more weak systems. So we're able to go toward both higher redshifts and also push towards slightly weaker systems. So we're able to really much more easily sample the population. Yes.
What's the difference between the open and filled points?
That depends on the significance of the detection. Yeah. So we were a little bit careful here, still going like we're not really entirely. I mean, it's sort of first pass essentially here, so we were not entirely confident. Immediately calling everything 100% reliable. For this one, we're calling it, yeah, definitely reliable. These are a little bit more sensitive based on the fact that they're quite low surface brightness. Yes.
Do you do like a sort of K correction, like the difference between the two frequency images that you showed previously? The morphology is quite a bit different. And so you go to higher redshift, you probe higher rest frame frequencies, right?
Correct. Yeah,
And
that's
so you have to
indeed one of the
make
sort of main sort of question marks indeed, like to what extent can you still, towards very, very high redshifts indeed, use those same frequencies. In principle, you can apply the K correction, but it won't necessarily affect the volume that you measure. It will, of course, affect the brightness that you measure, but we don't actually use the brightness at all. We only use the volume that we measure. So indeed, the assumption here has to be that even though we go towards slightly higher frequencies, we still are in a regime where we are sensitive enough to the complete structure. We do also want to extend this towards the LOFAR LBA stations in the very near future. So currently, we've been mainly using the LOFAR HBA stations, so the slightly higher frequency stations. That indeed has a bit of a risk of like potentially already going into this higher frequency rest frame regime. But if we can go down towards the LOFAR LBA and we can have both an LBA and an HBA measurements, then we can indeed say with much more certainty, like, yeah, this is actually the complete structure, yes or no? Yeah. So that's a paper from 2024. What we're currently doing is actually taking this one step further. What we learned in 2024 was that even though we have relieved the sort of main bottleneck, if you will, of those pressure measurements, of the volume measurements, we still need the ICM pressure, which is still a bit difficult to get. That's still currently the main bottleneck, essentially, if you go towards the higher redshifts. So what we did was we essentially included also the SE effect. So of course, that's the effect where the CMB photons essentially get upscattered or downscattered, upscattered by the ICM, which is a much more high energy than the CMB. And you can tell that you can sort of recognize that sort of shadow, if you will, on the CMB if you go towards the appropriate frequencies, which is sub-millimeter. And the really great thing about that is that if you previously got the pressure from the X-ray, you really needed to do some sort of like spectroscopy to get to the actual temperature. But if you use both a combination of X-ray and SZ, you no longer need any spectroscopy. You can do it purely based on total intensity maps. So the SZ actually gives you basically a sort of straight measure of the pressure. The X-ray gives you a measure of the approximate density, and if you divide those two, you can get to a temperature measurement really quite quickly. So it's really quite easy using a combination of SZ and X-ray to get a picture of the complete thermodynamics of the ICM. If you also add in the radio information, then basically with 3 simple observations, you can get a complete picture of both the heating and the cooling in a system. And we actually got that for a system at redshift 1.3. So this shows you here the WISE map with the BCG over there, 2 radial lobes on either side. And if you then add in both the X-ray and the SZ, you can combine that into this picture, which shows you the sort of approximate temperature map. And we see very nicely that coincident with this BCG, we have a sort of cooling core where this surrounding ICM gas can be seen to be cooling down, feeding this massive black hole, producing these 2 radial lobes in turn again. This combination is already showing to be very, very, very quite powerful. And if you put it in a plot compared to, similar to just before, you also very quick to see that this measurement is currently the highest redshift measurement that we have of the amount of like heating in a system. And it's also we're sensitive to slightly weaker systems as well. It's a really quite sort of low cavity power system as well. And we're currently expanding this also with a few more targets. So hopefully we will soon populate this region a little bit further and actually get a much better constraint of like, is there a sort of true trend where over redshift we see a sort of peak around redshift 0.4 to 0.6, and then a sort of gradual ascent almost looks like. Then finally, chapter 3 is on synchrotron threats. So one of the sort of mysteries, if you will, of recent radio observations is the detection of these very, very peculiar synchrotron threats. So this is an example taken with Meerkat. We have a very nice central AGN producing 2 large radial lobes on either side. And then to our surprise, there is a sort of collimated synchrotron thread connecting those 2 structures together. It's also 54 dB. I think this is a VLA image showing you also a classical case of AGN jets into opposite directions. then these larger radial lobes, and to our surprise, connected to this radial lobe are these two sort of very, very narrow filaments that just extend away from the radial lobes into seemingly empty space. So these are two examples of systems where, to our surprise, we find radio emission on a very, very fine scale, just seemingly sort of collimated into empty space. We currently also now have another example of this. This is Able 2199. Personally, one of the most fascinating sources that I've ever seen with LOFAR. So you again have the case of the AGN core over there producing these two larger radial lobes, and then there's a lot going on. There's the sort of southern bridge, similar to what I showed before. So it's sort of a narrow bridge connecting those two radial lobes. Then we have a combination of different sort of narrow threads as well. And most spectacular, this whole structure here on the western side, where we have all these very, very fine threads in this entire sort of threaded structure together. So that's another case of for some reason, there being this whole structure of very, very narrow collimated synchrotron emission. Fascinatingly, if you compare this to the previous BLA images, you'll find that they're simply not there at all. They're very, very visible, particularly these sort of Western structures. So it also highlights that it's really quite important to go towards the very, very lowest frequencies, like you have access to with LOFAR, to actually be able to recognize structures like this. Otherwise, you will just miss them at like higher frequencies. Also, to augment that, if you look at the X-ray image and you subtract a sort of smooth model from that, you see very, very beautifully that similar to what I showed before, most of these radial lobes lie inside of this sort of purple-ish region here, which is the sort of surface brightness depression or sort of cavity system, if you will. But just to our surprise and very, very nicely, we don't see any sort of dip here associated with these Western threads over there. We actually see sort of small increase in brightness over here. So we really do believe that these structures are not a sort of previous outburst that we're still seeing or whatever, but that it's really a sort of example of these threaded structures essentially extending away from what you might call a radial lobe and really being a sort of structure in and of itself. We then went on to do a bit of quick modeling to see what is actually the correct physical skill associated with these structures. I don't want to go into too much detail, but basically what we did was that we assumed that the structures were fundamentally like sort of cylinders of a uniform emissivity. We then took that cylinder, we convolved it with the size of the resolution of the telescope and matched that to the actual images to see, on what kind of physical scales would these threads have to be in order to actually match the observations. The results are over here in this quite basic corner plot. The key thing here is that in order for it to match up observations, these threads have to be on a scale smaller than 50 parsec, which is a really quite fine scale. Formerly, it also shows a sort of lower limit, but we really don't trust the lower limit on this one. It's really about the sort of upper limit here, which is that in order to match the observations, these thread structures really have to be really quite fine. And it also again highlights the value of like having different resolutions available to you, having the ability to see the complete structure, which is sort of arc minute scales. And then these sort of very, very fine structures, which are, well, below 0.3 seconds, actually, is a really quite important combination if you really want to see the complete structure of these systems. So we're currently in the situation that we have a wide different range of morphologies. We have these sort of connecting filaments between two radial lobes. These are around 80 kiloparsec long, about a kiloparsec wide, estimated, relatively steep spectrum as well. We have these sort of filaments protruding away from one of these radial lobes. Again, quite a similar story. A couple of 100 kiloparsec, again about a kiloparsec in width, and these sort of free-floating filaments, which don't really seem to almost like directly connect on either side. Maybe over here, for instance, but like over here, these basically seem to be completely free-floating in space, essentially. And these are on a scale of around 30 kiloparsec and less than 50 parsec actually in width. And again, also very, very steep spectrum, so you can really only see them at the very, very lowest frequencies. So the question that we're currently working on is, how do you actually produce these sort of threads? So we're currently thinking that these threads are most likely produced by some interaction with the radial lobe and the surrounding magnetic fields. So we're currently doing a systematic study to actually compare agent in different environments, all get images for these, and to really sort of see when do we actually find these threats and when do we not find these threats. That's a bit difficult because absence of proof is no proof of absence. So if you don't see a threat, that doesn't necessarily mean that it's not there. It just means that you weren't able to see it. So it's really quite difficult. It's not difficult to find threats. It's difficult to very confidently not find threats. So we're giving ourselves the sort of optimal conditions, which that we're looking at some of the very brightest radio AGN from the PCR catalog, only looking at like very nearby sources, so redshift limits of 0.09, and sources that we can actually observe with International LOFAR telescope, because we know that this is a really quite powerful tool. We have the low frequencies that we need, we have the resolution that we need, and we have the range in dynamic skills that we need. That gives us a really quite substantial list of targets to look at, and I won't go through all of these because it's really quite a lot. But what I can show you already right now is two beautiful examples. One is in a field environment, and one is in a cluster environment, and you can already see very clearly that these two sources have very different structures. In the cluster environment, we see this beautiful example where we have all these sort of filamentary structures all the way throughout the radial lobes. And in this field example, we do have, this very sort of bright hotspot region on both ends, which is quite typical of what you would expect. But most of these radial lobes actually are relatively diffuse, don't really have a lot of internal structure. So we think we're like on the right track with the magnetic fields environments being a really key parameter in all of this. What we're also doing right now is working on the LOFAR survey. So I just want to very quickly advertise that we're sort of following up on what I mentioned before, the LOFAR 2-meter sky survey. We're basically going through the LOFAR 2-meter sky survey, taking all of those observations and actually reprocessing those data, including the international stations. That's something that's really quite challenging from a calibration point of view. But now that we have much more experience with this kind of thing, we can actually go back through this and in a fairly automated fashion, reprocess those data and actually give you images like what you see here, for instance, for all of those fields. So in the very near future, those international baseline images are no longer hopefully expert only kind of things, but they're things that you can just hopefully get from the archive that we will be putting online very soon. And also, as I mentioned before, if we go towards also the LOFAR 2 era, one of the things that we will have is the ability to do joint observations between the LBA and the HPA. And we also hope that we will have better access to high resolution work in the LBA by combining it with the HPA, and therefore also have better calibratability between those two different antenna types. So hopefully in the near future, we can even go further than what I showed before, and actually be able to do both higher resolution and higher frequency and lower frequency work at the same time, which is going to be really key to actually study the physical properties of, for instance, these very narrow threads. So my main take-home messages are that, first of all, LOFAR has been really making some quite groundbreaking discoveries in the field of galaxy clusters. The ability to observe galaxy clusters at both low and high angular resolutions is really quite uniquely valuable to multiple science cases. And currently, developments like LOFAR and LOFAR 2.0 will also hopefully make it. Will also provide a lot of other fascinating opportunities to look at in the very near future, and of course also hopefully provide even more discoveries in terms of galaxy clusters in the very near future. Thank you so much.
Questions? There's also some people online, so.
I don't have the chat.
Thanks. You call these threads like filamentary structure, but how much sure of the geometry? Couldn't those be sheets, and you're seeing actually the bending of a sheet or something like that to resemble? I would imagine that it could be a shock or something.
Sheets are possible, but it would have to be quite coincidental that you're not seeing any other part of the sheet, but you're really only seeing the edge-on part of the sheet, right? So if you look at for instance, like here, for instance, it's you don't see any other sort of emission north or south of these threads. It's really just mainly the one thread here. Similar cases there, you can actually get RM measurements from polarization and actually get an estimate of their thickness, which also proves that they're indeed much more sort of filamentary structures. And also in the case of Able 2199 here, the main question here is mainly that it's kind of coincidental almost that these happen to be seen at basically exactly the resolution of the telescope. So it's much more of a question of like, do we actually have sort of distinct individual filaments, or is it much more of a sort of continuum all the way down that we just convolve with the resolution of the telescope and then it appears like a filament? But maybe, for instance, like in the Milky Way as well, in the center of the Milky Way, we have similar filaments, which are actually on a much, much smaller scale as well. So the question is, what if this is actually not? So for instance, like here, it looks like you almost pick up individual filaments, but is it really individual filaments, or is it even smaller structures that we convolve into filaments, if you will?
Questions? People online, feel free to put something in the chat and then we'll read it out. And in the meantime, Brian?
Just out of curiosity, have you looked at the effect on neighboring galaxies of these radio AGN? So like in the cavities, for example, is there less gas available to coalesce onto neighboring galaxies and satellite galaxies, or maybe it's cooler, so it's easier for cold flows to form? Might it truncate star formation or enhance star formation of those galaxies?
Good question. That's a very interesting idea as well. I'm not aware of like anyone actually looking into any sort of coincidence between the cavities and any random member galaxy. I think indeed that would definitely be very interesting, but I don't think anyone has actually gotten a clear example of knowing that a particular galaxy is located inside of one of those environments. But yeah, that would definitely indeed be a really interesting project as well. Yeah. I think also a question would be, can you actually prove that it's in there rather than just like line of sight? That's always a bit difficult because it might just be just in front of it or just behind it, or yeah. So it might be a little bit difficult unless you can actually immediately already see the impact that it has to prove that it's definitely inside of the radial lobe or not.
I've a large enough sample, then perhaps you can average over those.
Maybe, yeah. I think there's a couple of examples of sort of larger structures like giant radio galaxies, which are on a scale of like 700 kiloparsec or more, where you can sort of see them at some point colliding almost, if you will, with a galaxy. But those are really quite rare examples, and they're not really what you would call cavity systems either. They're much more just sort of outflows that end up just flowing into those areas and end up at some point colliding with something. But yeah, not something that I would call a cavity system indeed. Yeah.
I have an adjacent question if there are no other
Go for it.
questions. So higher redshifts, like redshift 2, which is still reasonably high redshift for me, and like 2 to 4, let's say, what effect do you think like radio AGN have on the like incipient ICM formation, like in terms of heating? I guess you have sometimes more powerful radio galaxies at these redshifts, perhaps preferentially found in protocluster environments. And so do you have any thoughts on how it might affect the evolution of the forming ICM?
Yeah, I think indeed it's really going to be key to sort of figure out like sort of chicken and like egg story, right? I mean, does the ICM form and do you then get the AGN turn on, or does the AGN already turn on before the ICM actually starts to form as one big entity? So I think a really key thing will be to look into the protocluster regime and to see like how do those sort of co-evolve? How does the AGN co-evolve with the formation of the ICM? I know that we have a few examples of very clear AGNs already operating at like redshift 4 almost. I mean, there's a few examples of that, but I'm not entirely sure to what extent they entirely co-evolve, or one of them is already definitely in place before the other one actually starts to form. I think indeed the AGN will most likely already be quite active because of gas contained within the galaxy itself. So I think indeed the most likely scenario will be that we already have the AGN quite active before the ICM is really forming. But I'm not sure if we have the exact numbers for that, but I think it will be really interesting to indeed see like if we can actually have a few more of these sort of radio images, and especially also the combining X-ray or like SZ to really see like over redshift the ICM forming and to really see the impacts of the AGN. I think that'll be really, really cool to see. Yeah.
Those redshifts X-ray is near impossible, but SE,
Yeah.
if you stare and stare and stare with ALMA, maybe you can get it.
Yeah, and also like for instance the one that I showed before. I'm not sure if I should even be trying to go back through all of this, but this image that I showed of the ICM, this also is SE. So you can definitely get SE up to redshift 2-ish. Beyond that.
Somebody beat that about 2 weeks ago.
Oh, really? Cool.
4.3.
What's the
Whoa.
Wow. Okay. Okay. So that's very, very encouraging. Yeah. So, but how long did it take for them to get?
It's, I think, the deepest ALMA data ever.
Okay.
Yeah.
Casual.
It's ACA and ALMA.
Oh.
Yeah.
Yeah. So that's going to be almost the main issue, is that getting samples is going to be very, very difficult, right? I mean, single targets is manageable. We've gotten a very small sample approved for Chandra for next cycle, fingers crossed. So we can hopefully get a few more sort of redshift 1.5-ish targets combined with the SE. We already have the SE now, so we now only need a bit of X-ray. But yeah, it's going to be difficult to build up significant samples, but I think it would be very, very worth to try. Thanks.
I'm intrigued by the possibility of that turnover that you mentioned in the I think it's the radio sort of jet power versus redshift, right? Like the
Is it the pressure thing?
This one.
yeah, exactly. Yeah. So any theoretical idea whether we would expect a trend there, or
Yeah, there is a trend also shown in simulations. I don't think it happens this early on, essentially, but I think we do expect that if you go towards a higher redshift, that more and more of these AGN turn into sort of quasar modes rather than radio modes, and that indeed does cut down on the amount of like cavity power systems with high cavity powers. You do need essentially the kind of right amount of Eddington ratio, about 1%, to actually produce really good radio mode feedback. If you go towards higher redshifts, then typically we believe that we're going more towards quasar mode typically. So then you end up with fewer systems. So in that sense, it's not necessarily unexpected, but it's very poorly constrained when it actually happens and like how this actually follows. You know.
The quasars turn on and off, and you might just see it in a different mode.
Yeah, maybe you'll see sort of quasar mode and a very brief burst of like radio mode, and then who knows? But yeah, I think indeed there's some cosmological simulations that actually do show a similar trend, but I think that they still had like massive question marks on like and what redshift would you actually expect things to happen and like all of that, you know.
Roland, I just have one question, actually two. The first being, is there an equivalent to the LOFAR array in the Southern Hemisphere?
Not entirely. They're currently building SKA low, which is going to be similar to the Dutch LOFAR array, essentially in terms of like the scale. Of course, much more sensitive. They'll have much more area. What we are considering is to extend SKA low with what we call Lambda, which is the low frequency Australian megameter baseline demonstrator array, which would be a quick array of like 4 to 6 stations to essentially extend SKA low up to the kind of scales of like LOFAR. But then of course it's a good way to sort of probe into that regime and to hopefully, you know, demonstrate that there's a need to go towards higher resolutions and hopefully get more funding for SKA, even though I think that will be difficult right now. But that's indeed the current plan, is to try to build a few more stations at longer baselines compared to the SKA low, which will essentially mean that you will have a very, very dense core for SKA low, which will be very, very sensitive, and then a few longer baselines giving you access to some high resolution observations as well. But it will not be as coherent essentially as like LOFAR. LOFAR has a quite nice sort of range of baselines where it goes from nice short baselines to a little bit longer, a little bit longer, a little bit longer, all the way down to very, very long. And I think SKA low plus Lambda will be a lot of short baselines plus a few long baselines. So,
I see.
yes. But yeah, that's indeed the closest we will get to a Southern Hemisphere LOFAR.
Interesting. Okay, thank you. And then one other question, how would Gemini benefit your science, with the optical near infrared capability? I mean, what would you need from Gemini to complement what you've shown here with LOFAR? Where would you take advantage of any of the instrumentation on Gemini that we currently have?
That's a really good question. I think it will mainly come down to actually observing the connection essentially between what goes on in the environment of a galaxy and actually what goes on at a central supermassive black hole. I think we really need to better understand how essentially all of these surrounding gas from the environment of the ICM accretes onto those galaxies, start to form stars, starts to feed into the supermassive black holes, and then in turn produces the supermassive those jets that we see in the radio. So I think one of the sort of key things that would definitely be quite helpful, although I don't have any Gemini programs in the sort of list right now yet, is to definitely look at a few more of these sort of really interesting systems like the one that I showed here, for instance, and get a much better picture of like what actually goes on in that galaxy, in that BCG, where we have the cool core forming around the supermass around the galaxy, which then feeds into the galaxy itself. And I think indeed one of the reasons why we even bother doing HM feedback in the first place, of course, is because this feedback cycle is really important to balance in the system. We have heating and cooling, and we need to know how those are in balance to figure out like what actually is the environment going to be like. But in the end, of course, it all comes down to better understanding galaxy evolution, better understanding the supermassive black hole evolution, and of course, yeah, it would be really good to tie in the feedback picture essentially with actually what goes on in terms of like the galaxy evolution, and complete that picture that way.
Great. Thanks, Roland, again. Thanks for coming. That was fun.